All right, good morning, everybody. So as promised, today we'll have more theory. So we'll have one-dimensional and three-dimensional structure of the nucleon today, but of course, those of you who want to have experiments, don't fear. We'll have an experimental lecture as well. And we'll have a tutorial related to extractions of Barton distribution functions from the experimental data. I'm very happy to have Pavel Nadolsky from Michigan State University here with us. He's going to tell us about collinear structure of the nucleon, in particular about Barton distribution functions in the era of Electron-Ion collider. Floor is yours.
Well, thank you, Alexei. Well, so I'm very happy to be here. Thank you for coming to my lecture. And as Alexei said, we will today we'll start talking about QCD theory, and I will start with the simplest non-perturbative functions in quotes, which are collinear Barton distribution functions. And I was asked to specifically focus on the aspects that will be relevant for precisely measuring the hadron structure at the electron-ion collider. And so maybe the first thing I would like to emphasize is that well, you probably, from the discussions on the previous lectures, you probably already have a general picture that our particle accelerators, colliders, really work like a massive microscopes. So what they really do is that they zoom in on subatomic structures and see finer and finer details of the subatomic structures. The first kind of measurement of this kind was done by Rutherford, who saw, who saw a point-like nucleus inside an atom, right? And so then as we increase the energy of our colliders, you could imagine that literally these experiments work like microscopes. So they zoom in on smaller and smaller parts of these small objects. And so therefore increase the energy of our scattering, meaning that we reduce the typical Compton wavelengths of our probes. We see smaller and smaller structures. So therefore, like 1950s, about 100 years ago, people started seeing protons and neutrons inside the nucleus. And then if you zoom in on the individual nucleus and you go kind of smaller and smaller boxes, as shown here, you see smaller and smaller structures, right? So literally, you could imagine you kind of look at the nucleus by eye, and initially it looks gray, but as you start looking at the nucleon, you start seeing, constituent parts of the nucleons which are initially colorless. So they they're kind of grayish. But now if you keep zooming in, so you realize that these constituents have their own substructure. And so this substructure is given in terms of the small components called quarks and the gluons. And so here we really say that they carry new kind of fundamental charge called color. And so therefore, interactions of these quarks and gluons are described by a fundamental theory called quantum chromodynamics, right? So this is hopefully something that is familiar to you. So the other thing that is you already heard many times is that if you hit the nucleon with a very short wavelength probe, so these quarks and gluons are interacting very weakly. And so we say that they are asymptotically free, their QCD coupling becomes small. And so this is kind of the big picture that you have to imagine that when we discuss, anything today and during these coming days, basically the interaction between partons weakens when we go to very small, high energies, meaning going to very small wavelengths or small resolution scales. Okay. Now, the other thing about these colliders is that they don't just see the whole object at once. So what you could really imagine is they really work like a microscope, but they take a snapshot of one pixel at a time. And so the pixel can be large. So then you'll see only the whole nucleus or the whole constituent quark, right? And so constituent quarks, well, there will be, let's say, about 2-3 constituent quarks inside the nucleon, right? But now when you decrease the size of the pixel, increase the resolution, you start seeing more and more structure. But because we take these pictures in pixels, so somehow we cannot easily visualize these objects, and that's why we are interested in doing the three-dimensional photography, which is a kind of technically challenging procedure. But what we do, therefore, is that we describe the properties of these objects using correlator functions, non-perturbative functions. And again, you will hear me a lot about them in the coming days. The most complex ones are called Wigner functions, but then they can be various kinds of functions that will depend on all possible quantum numbers of the quarks and gluons. They will depend on the flavor of the quarks. They will depend on the momentum fraction carried by the quarks. They may depend on spin, transverse momentum, and so on. Okay, and so what I will discuss today, I will discuss the simplest kinds of most well-known pattern distribution functions. Well, so basically the next two lectures are just sitting in this small corner here. But what I would like to emphasize to you, even though we sit in this small corner, in fact, we still have lots of very interesting results and phenomena that describe these pattern distribution functions. And the reason is the following. So these pattern distribution functions are the simplest in QCD theory, but we really study them a lot. And so therefore, there is lots of very intricate information that describes these pattern distribution functions that, at the high precision level. And so therefore, the data science or the information theory that describes these pattern distributions is the richest, because really we try to measure these pattern distribution functions, let's see, with the accuracy about a couple percent. Okay, so I'm talking about here about unpolarized PDFs, but you basically, when we go to the EIC era, let's say 10 years or 15 years from now, all these aspects of information theory will also apply to many spin-dependent or nuclear PDFs. And the important point here is that these functions describe the structure at typical energy scales, which I'll call Q, above 1 GeV. Okay. Okay, so then my plan today is just to first introduce you to theory. Then today we'll talk about experiments that measure pattern distribution functions. Please do not hesitate to raise your hand and interrupt me. We have time for the discussion, right? And so far so good. So everyone kind of following what's going on here. Yeah. Okay. All right. So therefore, let's talk about the way how these pattern distribution functions are introduced. Well, I work a lot with the data from the Large Hadron Collider. And so today I will have many examples coming from the LHC, but I also have some examples from fixed target experiments. And the basic idea for introducing PDFs is the fundamental method of quantum chromodynamics called factorization. Right. So, for example, again, sorry, I have here an example about that is related to Higgs production, which was the main discovery at the LHC. But you could imagine that similar ideas will apply to various measurements that we do at the EIC. Well, let's take any kind of process where we have this high resolution scale, right? So, for example, the Higgs mass is about 125 GeV. So, therefore, it sets a very high resolution scale. And then, if you you probably take any QCD textbook, they will start discussing so-called pattern model that allows us to calculate the cross sections for scattering in this kind of situation, which will tell you that if the resolution scale is high, so we can factorize the whole cross section for proton-proton or hadron-hadron scattering into what is called a hard cross section, which is given by a simple diagram, which only has one or at most two incoming partons before the hard scattering. And you need to multiply this hard cross section by probabilities for knocking out the partons. Well, in this case, so they are gluons from the incoming hadrons, right? And so again, so hadrons here are protons, but you could imagine they can be nuclei, pions, etc. Okay, so that's kind of the big picture. So then now, in terms of this Kalini factorization, well, it works not just at the leading order, And so again, the leading order is what we call the pattern model. But this collinear factorization also works to all orders, except, as we go to high and high orders, so this factorization becomes more and more complex. But roughly speaking, again, we can come back to that. So we write the Hadron scattering cross section as a convolution of our hard cross section. Well, and then in this case, with two pattern distribution functions. And so this formula is shown to all orders in perturbative QCD. Let me explain a little bit what the pieces are. So I already mentioned to you the sigma hat, the hard cross section. We can compute it order by order in the QCD coupling that generally depends on renormalization scale, mu r, which must be large, right? And then we multiply this hard scattering cross section by two pattern distribution functions. And so the pattern distribution functions will depend on the flavor of the pattern. They will depend on the momentum fraction, which will be called the x of c, depending on the notation, at another scale, which is called factorization scale mu f. Okay, and so mu f is generally close to mu r, but it does not have to be exactly equal to mu r. Okay, all right. Now, the important thing to realize here is that let's quickly talk about the notation. So we have measurable kinematic variables, right? So, for example, we could measure the invariant mass of the Higgs boson, which we'll call Q here. And so Q will be my measured hard scale. And then we can also measure quantities that, for example, will depend on the rapidity of the Higgs boson. And so there are so-called Born level momentum fractions called x1, x2. Okay, so these quantities are measurable. Q, and if you measure rapidity and Q and the invariant mass, you measure these quantities. But if you go to beyond, to the orders beyond the leading order one, so you need to integrate over momentum fractions that come in. And so these momentum fractions, here are at XC, now, it should be XC here. So they are partonic momentum fractions that are integrated over in general. And so at the lowest order, XC is equal to XA, XCB is equal to XB. But at high orders, we generally integrate over. And mu f will be set equal to this Q scale. But mu f in general is an arbitrary scale. So the mu f, does not have to be exactly Q. It can be, let's say, a fraction of Q, or it can be some other, hard scale. Okay, so therefore we have this very interesting situation that we measure certain properties, and we must have the hard scale, but then we also introduce arbitrary scales that must be included here. So then mu f or mu r is naturally said to be our order Q. And the other thing is that there are always power suppressed terms, and that's maybe something will be discussed later. So now what's the purpose of this arrangement? The purpose is that in general, if mu is very different from Q, sigma hat will have large logs, right? And so these logs will scale like alpha s to some power times the power of the log of Q squared over the masses of the quarks. And so these quarks, large logs can be large. So therefore, this picture may not converge well in perturbation theory, but if we write the factorized picture, we are able to resum these large logs to all orders in perturbation theory. Okay, and so the way this works then, and again, probably you'll hear that, is that first of all, PDFs, pattern distribution functions, we cannot compute them yet completely, right? But first, they have a definition. So the pattern distribution functions are defined for each type of pattern and hadron. And for example, here is a definition in the so-called MS bar scheme for quark pattern distributions in the inside the proton. Now, all of these definitions, they will correspond. They work in such a way that the PDF is literally equal to the number density or the probability density for finding a pattern A inside the proton at the leading order. But beyond the leading order, they do not have to be probability densities, right? And so then the very challenging thing to show is that this for any given process, you can actually write this factorization formula because it is not a given. So there will be processes where this naive factorization will fail. But for example, at least for simplest processes like the trillion process with one factorization scale, well, the factorization in terms of these universal PDFs works quite well. Okay. Okay, now the other thing that you probably also have heard that in general the pattern distributions depend on the momentum fraction x of c that is carried by the pattern, but also they depend on the scale mu. And so we cannot really calculate the dependence on x, but the dependence on mu is known very well. And so it is given by so-called Tokschitz-Gribov-Lipatov-Altarelli-Parisi evolution equations, with the kernels that are now known to a very high accuracy. They are known almost completely up to 4 loops or N3 low accuracy. Okay. Okay. So now this evolution therefore works extremely well, precisely in these calculations. And let me quickly show how this how this evolution behaves. Well, first of all, these are the typical shapes of the PDFs that you will encounter in essentially any analysis of PDFs. So, so let's compare here PDFs for up-down quark, which are given by the black and red line, and the PDFs for the gluon and SC quark. Okay, so now one thing that you will immediately see is that the PDFs for U quarks and D quarks in the proton, well, they peak at about index of about 1/3. And this simply reflects the fact that, well, there are two U quarks and one D quark in the proton at the lowest scale. So therefore, therefore you do expect that there will be excess in the PDFs at about 1/3 for this for these quarks. But on the other hand, so you do not see exactly the delta function at x equal to 1/3. What you really see is that the shapes are smeared out by the evolution effects. And so the typical effect of the evolution is to take the probability from the high x and put it to the low x. Okay, so let's see how this works. For example, we take the up quark just here, right? And so here I show the up quark at Q of 1.3 GeV, right? And so let's see how it evolves. So this will be the up quark at 2 GeV, 10 GeV, and 100 GeV, right? So what you see basically is that you have the reduction of the probability at x above 0.1, and you have a rapid growth of the probability at x below 0.1. And so there is this kind of sweet spot where the like x about 0.1, where the quark PDFs almost do not evolve, right? And so that's kind of an interesting place. Okay, now let's look at the other PDFs. For example, here is a PDF for the up U bar and the gluon from two different sets. These are all sets, CTEC and MSTW. Now, as you see that, well, U bar is, at small scale, behaves relatively flatly. But for the gluon, it's small scale, in this case, 1.3 GeV. Actually, you see the very, very strange behavior where the gluon can even go negative. Okay, and so you say, okay, how can we have the negative probability? Well, what it shows here is that somehow our perturbation theory does not work at small x. And so therefore, you can find phenomenological parameterizations for gluon PDFs which go negative at small x. Okay, so this is again at Q equal to 1.3 GeV. Now, the other thing is that this is the linear scale. So let's plot this on the logarithmic scale. So this is the same plot on the logarithmic scale. So now let's see what happens when we evolve PDFs to a higher scale. Well, so this is for 2 GeV, 10 GeV, and 100 GeV. Okay, and so you see a couple of things. Is that first of all, the PDFs are positive everywhere, so they behave much better at a high scale where our perturbation theory is stable. So there were logs of 1/x, which were very important at small x, and they destabilized perturbation theory when the scale was low. When we evolved it to a high scale, alpha s became small. So the PDFs now behaves as they should. And also look, the parameterizations, two different parameterizations of the gluon agree much better now everywhere, right? So this indicates you to that the perturbation theory stabilizes. Okay, all right. So then, okay, so therefore now what we see is that basically the decoupled evolution works very well. So therefore, we can play the following game. We could say that the PDFs are universal. They depend only on these parameters, A or I, X and Q. We could parameterize these PDFs at a low scale of about 1 GeV. Let's call it the scale Q naught. And then we can predict them at all other scales, at higher scales, by using decoupled evolution equations. So then the game is to determine these parameterizations, which typically will have a form that is shown here, okay? All right, so, okay, and then of course, once we found these PDFs, we can make predictions for all kinds of processes. We could take, well, for the EIC, we will have lepton-hadron scattering in general, where we have one PDF for prediction, but for hadron scattering, you have 2 PDFs for each prediction, okay? And so then whenever we calculate sigma hats to very high accuracy, we must have the PDFs that match the accuracy of the sigma hats, even though we obtain PDFs not by calculating them in perturbation theory, but by fitting them, okay? And so that's where you see the challenge lies, because we can calculate the sigma hats very precisely to, well, now related to accuracy of about 1%, but then somehow we need to set up determination of PDFs, which is really the kind of the big data analysis, if you like, to the same kind of accuracy. And so you need to deal with different kinds of issues to control uncertainty on PDFs. Okay, and so this is just an example of multi-loop calculations that are done now. I will not spend time on this. And so then the big question is that where do we find the PDFs that will match the accuracy of our hard cross sections? And so let me ask you that, okay, so suppose you need to do the calculation. So where will typically your PDFs come from? Let's see. So what would be your suggestions? Suppose now you, okay, so that your advisor asks you, do the calculation for some process. So where will you go to get your PDFs? Or where will the PDFs will come from? Did anyone do such calculation yet?
In CTAC.
Huh?
In CTAC.
In CTAC, okay, so but what do you do?
Well, if I do an NLO calculation, for example, I use the PDF that are based for the NLO calculations.
Okay. And so where do you get them? Or
Well,
where do they come from?
LHE PDF.
LHE PDF, right? So there is a big library called LHE PDF. Okay, so therefore, if you are not sure, you just go to this library, look for LHE PDF, right? And now, okay, so then you go to this library and you have literally like thousands of PDF sets. Okay, so the next question to you is that, how do you decide which PDF set to use? So did anyone run into this problem yet? So you go to LHE PDF, but you don't know which PDF sets to use. Didn't encounter, right? Okay, so basically, okay, so you know there are many ways to load the dishwasher, right? So there are even more ways to produce PDF sets. Okay, and so that's kind of what you have to, that's why you need to practice a little bit to think about what different PDF sets give you, because you can generate PDFs in many ways, right? And so now the big picture is that, well, typically we determine PDFs from measurements, but there is no single measurement that will measure all PDFs. Even the EIC will not measure all PDFs. And so what you really do is that you do a big data analysis where you have contributions from big experiments like LHC and Tevatron, mid-sized experiments like HERA is a very important one. And then, of course, there are fixed target experiments, which are, okay, you would say they are old-fashioned, but they are still very important. And I will try to convince you why. And so then increasingly we get contributions from first principle calculations of PDFs from lattice QCD. And so like 10 years ago, we just had the smile of the cat but now the cat actually becomes more and more physical. So you actually get more and more precise predictions from lattice QCD. But then you ask a question: are the PDFs that come from lattice QCD, are they exactly the ones? Do they exactly match on the PDFs that come from fixed target experiments, because or experiments in general? Because you will see there are some issues related to that. Okay. All right. So, but now, if we just would like to derive the PDFs from the experiments, so we need to do what is called the global QCD analysis, which has this very standard procedure. Okay, so first of all, you take most precise measurements, which you believe can constrain the PDF. And so this is shown here. And so then you need to get very good theoretical predictions for this data. And then you feed these PDFs to this data. You find some shapes, and then you make predictions for new processes, okay? And so once you understood these new processes quite well, you put them back into the global analysis, and you kind of repeat this cycle, right? So in the hope that the cycle will converge at some point to some very precise predictions. Now, the other thing is that I would like to emphasize is that the data, but also theory predictions and the analysis have uncertainties. And so therefore, whenever you do this analysis, you need to estimate uncertainties on your pattern distributions. So it's not just one line. You will have a family of lines that represent uncertainty. Okay, and so an important point that to remember is that just like the dishwasher can be loaded in many ways, so there are many ways to estimate the PDF uncertainty. Okay, all right. Now, what I will talk about today is that we'll refer quite extensively to the analysis from our group called CTEC-T, or Tung et al. Group, which is releasing the new set of PDFs called CT25 next to leading order. And you can see basically this PDF set comes on the, well, is a new member of a big family of feeds that increasingly include more and more data points from various analyses as time goes by. Right, so right now the CT25 set includes about 4,050 data points, which include the data which was available in the previous PDF feed called CT18, but also includes 13 precision LHC data sets, sequence data, and as I mentioned, these PDFs are provided with uncertainties, right? So so what you see, therefore, again, if you look at this plot here, showing PDFs at 2 GeV. Well, some of the flavors are known very well, but other flavors, for example, the gluon, are not known well at all in some regions, right? And so now the LHC will sit somewhere here. So therefore, the LHC will be working with quite precise PDFs. But then again, if you're looking for some small effects, even though you have precise PDFs here, there may be effects where the uncertainty on the PDFs is still, well, non-negligible. Okay. All right. Yeah.
If you go back to the data shown, what's the W cut?
So the W cut here in this plot is, I think it's to 12 GeV squared. Right. So therefore, there is of course, CTEC JLab and GEM analysis, then they will use much lower W squared, right? And again, sorry, I will talk less about those analyses because obviously there is this whole discussion that we could discuss, well, how W squared and other small energy effects affect the PDFs. I'll talk a little bit about it a little bit more tomorrow. Okay. So today I will talk again about more kind of classical measurements and also about high energy collider measurements. Tomorrow we'll talk more about the EIC specifics. Okay, now let me ask you the question. So this is just to be sure that you follow. So, well, standard model has like I think 12 fermions and 4 bosons, right? 4 W3, yeah, so 4 bosons. So among these particles, which particle can have its own PDF inside the, let's say, inside the proton? So let's. Which particles of the standard models can be called partons? Okay, let's start with the obvious. Gluon is a parton. It can have its own PDF. UND, strange. Charm. But charm is heavier than the proton. Is it okay that? So what do we?
C quarks. C quarks.
The what?
C quarks.
The C quarks. Okay, so but C quarks. Okay, so what I'm trying to say is the proton is that it has a mass below 1 GeV. The charm has a mass of 1.3 GeV. So then can you have something massive? That is more massive in a less massive particle.
Small time-scale pair production.
Yeah. So okay. So basically, you have fluctuations, short-lived fluctuations inside the proton, and if your scale Q is large, much larger than 1 GeV, then you can have charm pairs, charm and the charm pairs produced inside the proton. So therefore, bottom has its PDF. Okay, how about top quark? So like if you take a typical PDF set, will it include the top quark PDF?
Yeah, but yeah,
Yeah.
That's a huge mass. So the global analysis fit is typically done with the lower energy. No?
Yeah. So basically, what happens? You have to decide if the particle's mass is comparable or much smaller than your typical hard scale. So if the hard scale is an order of the mass, you will say that this particle just sits in the hard cross section. If the scale is much larger than the mass, this means that can be a log of the hard scale, very high resolution scale divided by the mass, and this can produce a log that can be resummed in the PDFs. Okay, so therefore the top quark, you can introduce the top quark PDF, but typically you will do it for, let's say, very, very, very high energy colliders. But even for the LHC, this is typically not necessary, right? Okay, so what are there any other particles that can have its own PDF? How about electromagnetic electroweak particles? Can they have a PDF? Like, did anyone work with the photon PDF? Yeah, so basically, for example, the quarks can radiate photons very easily, right? And so therefore, now, of course, the rate of photon radiation is much smaller than the rate for the gluon radiation, but you can introduce the photon PDF, and so that's completely normal, right? What about W and Z PDFs? Can you have those?
Yes, we run into the same problem as the top quark or the heavier quarks.
Right. So actually, for the FCC, you may want to have W and Z PDFs, except it is much more difficult to set up the proper factorization for W and Z PDF because of electroweak symmetry breaking. But people are working on that as well. Okay. Okay. And so, of course, for the leptons, you can also introduce PDFs and PDFs, but those will be very small. Okay. All right. So that's okay. So that's one question. Now, the other so basically, this slide summarizes it. Now the photon PDF actually now is included in many analysis, and so I just showed you the examples. About 10 years ago, there was a breakthrough which allowed to calculate photon PDFs very precisely from the whole DS cross section. And the whole DS cross section is measured very precisely. So therefore, the photon PDF, in fact, even though it is small, but it is known probably is the most precise PDF among all PDF flavors. Okay, and so this PDF, the approach called LUX QED approach, so it really made a huge difference. The analysis before the LUX QED, like for example in CT14 QED analysis, there was a huge range of uncertainty on the photon PDF. After you put in the LUX QED PDF, and so this figures illustrate this a little bit. Well, so in this figure you compare the LUX QED PDF, which is just this line, and so this line includes the uncertainty, with the uncertainty that it was coming from the PDF, from the fits of the photon PDFs before LUX QED, right? And you see it dramatically reduce the uncertainty. And so this figure shows the differences between various parameterizations of the photon PDF. And so the differences are really just a couple of percent. So regardless of what you do, so really the photon PDFs are known extremely well, even though there are only few experiments that can directly probe them. Okay, now there is another question that I will save for maybe for the recitation or for tomorrow. Imagine I give you some QCT observable. So how can you estimate what drives the PDF uncertainty for this observable? Okay, so I do not ask you for an answer now, but this is something that will certainly come up tomorrow, and maybe we can discuss this at the recitation. So what would be your technique to estimate the uncertainty PDF, or predict which flavors drive most of the PDF uncertainty on the observable? Okay, all right. Now, in the remaining few minutes, I would like to quite quickly discuss the experimental measurements that constrain the PDFs. And so if you take the data that goes into, let's say, CT25 analysis, well, so the data sets fall into several classes that are shown here. So let's quickly go through them. So first of all, there is a big class that comes from inclusive deep inelastic scattering, out of which we have two subclasses. One are the fixed target DS experiments, so that will typically probe large momentum fractions and low resolution scales. So everything is plotted here as a function of x and mu. And then there is a much wider range covered by deep inelastic scattering at HERA, which probes the PDFs all the way down to 10 to the negative x 10 to the negative 5. Okay, so now this is kind of actually these experiments are probably provide the most precise information in all analysis. Now, I guess you will have a lecture about explaining how deep inelastic scattering works. So there can be a scattering using the photon, the neutral current, deep inelastic scattering, and also the scattering with the parity violating W plus minus current, so the charge current scattering. And so they probe different combinations of the PDFs. Okay, so that like now the HERA measurements are actually but for now they are most complete measurements and most precise measurements of the structure in the deep inelastic scattering. And so on the left hand side here you see the data for the combined data for neutral current measurement. On the right hand side you see the data for the charge current measurement. So basically these data sets are sort of the core data sets in our analysis. Okay, now, but these data sets are not sufficient for measuring the structure. And you can quickly see why. Well, imagine we look at that picture of the deep inelastic scattering. So let's look at the leading order. So in this case, our boson couples to quarks and antiquarks. And if it is a photon, so the coupling will be proportional to the electric charge of the quark or the antiquark, which means that now if we just look at the leading order, so the PDF, so basically if you write the structure function, so the structure function will contain contributions from various flavors. So the contributions from up-type quarks, up and charm, and the antiquarks, will be proportional to the fractional charge of the up-type quark squared. So the fractional charge is equal to 2/3. So therefore, the U and charm PDFs will be multiplied by an overall factor of 4/9. For the down quarks, which means down, strange, and bottom, you have minus 1/3 squared in front of this combination. So therefore, the down type quarks, just because of the charge, is suppressed by a factor of 1/9 over 4/9, so basically 1/4 compared to the up and charm, right? So what you immediately see, therefore, is that at HERA, it's very easy to measure up type and even charm contribution. It's much harder to measure down type and strange. So the HERA will just measure the whole combination, basically, right? So the neutral current. Well, then you need to introduce something else to perform flavor separation in this combination. Again, if you work at the leading order, so what you could say, let's measure the DAS on an isoscalar nucleon, right? Nuclei, for example, on the deuteron, right? So if you measure the DS structure function on the deuteron, well, now you switch, you assume that proton and neutrons have basically are related by the charge symmetry. So therefore, if you calculate the same leading order combination, so all flavors are multiplied by the same factor of 5/9 in the isoscalar target. Okay, and so therefore, if you now measure these combinations together, hopefully you will resolve some of the degeneracies, right? And of course, you can put in the charge current DAS, and so the charge current DAS will measure these combinations if you produce neutrino nucleus scattering. Okay, so there is some hope that you will resolve this, but of course you have to remember that you will probably be sitting in some constrained X range where you can measure all of this together, right? Okay, now you also say, okay, now what happens when we go to the high order? Well, at the high order, it's a couple of things, very interesting things happen. So first of all, at the leading order, so the photon doesn't couple to the gluon. But at the high order, you start picking up contributions from the Bjorken scaling violation from the evolution of the PDFs. And the evolution of PDFs is dominated by the gluon contribution. So therefore, by measuring the Q dependence of the deep inelastic structure functions, you actually can extract some information about the gluon. For example, Hera measurements of the low X gluon, they provide the tightest constraints on the gluon in Higgs production region, simply from the scaling evolution, right? And now you can also measure other combinations of flavors, but perhaps again, the important thing is that DAS, inclusive DAS on its own, cannot really resolve all contributions. And so that's why you see some analysis which will only work with deep inelastic scattering. They can show you very small uncertainties, but what you have to remember is that the uncertainties are small because the PDF parameterization is quite rigid. It's not very flexible. So if they were to explore the full parameterization dependence in this case, well, you must come back to the situation where you only measure some combinations of these flavors very precisely. If you see small uncertainties on the rest of the combinations, that's probably an effect of some inflexibility in the PDF parameterization. Okay, so therefore, therefore, if you really would like to separate the flavors, you have to go to the fits where you include additional measurements besides inclusive deep inelastic scattering. Okay, and so let's see, and so that's why we include these additional experiments that go into CT25 analysis. What are those? So we could include semi-inclusive deep inelastic scattering, like for example, the classical one will be you measure the part of the inclusive DAS sample where you tag a charm quark or anti-quark or charm meson in the final state, right? And so that actually resolves the gluon and maybe some so-called intrinsic charm contributions that I will discuss. You can include lepton production, lepton pair production, and nowadays you include lots of data from inclusive jet production, as well as from the other processes, TT bar, W charm. You can have CDs for light quarks, and so there are many other processes that people consider for this analysis. But what you have to remember is that the more experiments you include, the more complex the analysis becomes. So the more uncertainties, sources of uncertainties can contribute, and you have to basically be very careful with how you estimate uncertainties. Okay, now, Alexei, so how much time do I have?
Lecture is 1 hour.
Yeah.
We have half an hour coffee break after.
Right.
And principally, we have questions after the lecture. So when you finish your first lecture, you finish your first lecture.
Okay. All right. So then, very quickly, I kind of highlight a few things, and then I'll discuss them about during the Q&A. Okay. So there is this very interesting question about the flavor separation in the quark sea. Okay, and so naively you will say, okay, so both U bar and D bar are produced through decoupled evolution. You must have more or less the same U bar and D bar PDFs. Well, it turns out there are many things that can happen inside the proton that can introduce an asymmetry between U bar and D bar PDFs, but also you can break the charge symmetry between, let's say, the C quark PDF and C anti-quark PDF. And so even in the DGLAP kind of conventional perturbative evolution, you can break you actually do break the equality between C and anti-C PDFs, right? So simply from the evolution. So therefore, if you go to very high accuracy, you can actually, well, you definitely must resolve this kind of differences in between different CPDFs. Well, there is another interesting aspect of this is that you ask, well, how do you produce these PDFs? So there are so-called two mechanisms. One is so-called extrinsic C production. And so roughly speaking, this is the production of C quarks and anti-quarks in pairs through the gluon radiation. But you could also have so-called intrinsic C contributions. And so that, well, how do you understand the intrinsic C contribution? Well, let's imagine instead of the proton, we will work with the charm pentaquark. And so then in that case, you will, okay, so in the traditional picture, let's say for the proton, so that you only produce CC bar pairs through fluctuations at very high scales. But for the pentaquark, well, clearly you can have a charm quark inside the pentaquark at the low scale. And so this will correspond to so-called intrinsic contribution. And then if you say, well, maybe the proton as a whole can excite to a higher state where you have a CC bar kind of bound loosely to the proton, well, you can also have the intrinsic charm inside the proton. Okay, so therefore you can have these two mechanisms. Yes.
Does say the same idea as connected C and disconnected C?
Precise. Yeah. So basically, it's actually very. That's the next point is that this is actually quite closely mapping on the classification of connected C and disconnected C in lattice QCD, right? So disconnected C is basically what we call extrinsic, and intrinsic will be the connected C contribution. Well, and then there are studies, for example, this is a very nice study that say, okay, well, if you look at, let's say, the behavior of U bar plus D bar, you could have two components in principle. And so at low precision, you measure both the extrinsic and intrinsic components together. But in general, these components could have a different X dependence. So therefore, if you go to high enough precision, you may start seeing some kind of features inside U bar plus D bar that will distinguish between extrinsic and intrinsic C, right? And then there was another very extensive discussion recently about the magnitude of the possible intrinsic charm, and which can be in principle be present in the PDFs. And so the long story short is that well, this is a pretty small contribution, and we still don't know with certainty whether there is intrinsic charm or not. Again, this is something that we can discuss during the recitation, but basically our group comes to different conclusions compared to the NNPDF group about the possible existence of the intrinsic charm that can be already seen in the current data. Okay, now, of course, you can also constrain the C quarks and anti-quarks from Drell-Yan pair production. And so let's quickly take a look what happens in the Drell-Yan pair production case. Suppose I get a proton on a generally defined hadron or nucleus where capital N can be the proton, deuteron, can be iron, isoscalar, copper, etc. Well, if you write down the leading order prediction for this cross section, you see that you always have combinations of the quark PDFs with the anti-quark PDFs in the cross sections, and they are weighted by different factors. In the case of lepton pair production at low Q, where they're dominated by the photon, so which means that you do have sensitivity to CPDFs in this case, right? So now, if you assume, okay, so this is the expression for the proton-proton Drell-Yan pair production. Now, if you look at the scattering of the proton on the neutron, so you will have a very similar combination, except, okay, so instead of the combination U bar, you'll have a combination of UD bar. Okay, and so therefore now if you measure these two quantities together, well, maybe you can cook up a ratio in such a way that you extract the combination of U bar over D bar, or D bar over U bar, and that's how you can measure the asymmetry between the let's say D bar and U bar, right? So therefore, now, for example, you could take the deuteron and assume that in the first approximation, you neglect the binding corrections inside the deuteron. Well, and then you can take the limit of the large rapidity or large XF, XL much larger than XP. And you also assume that the up-type valence PDF is about 4 times larger than the down-type valence PDF. Okay, so then if you write down this expression, for example, you could take sigma PT over to sigma PP, and you use this leading order formula. So you can see that you can measure a quantity which is called R, which is simply D bar over U bar at large XP, right? And so large XP can be order 0.1. Okay, so therefore the Nadolsky experiments measure this quantity, the ratio of the proton deuteron to twice the proton-proton cross-section, and they can determine the ratio U bar and D bar. And so a few years ago, there was a measurement called E866, which showed that this ratio sigma PD over to sigma PP, well, it's actually not equal to 1. It has a strange shape whereby it gets very large at about 0.15, right? And so meaning that the D bar over U bar is not equal to 1 at 0.15. So which was kind of a big discovery. And so a few years ago, there was another measurement called Sequest or E906 measurement, which roughly verified this behavior, even though it wasn't exactly the same behavior. Okay, now you can also measure this kind of distributions in charged lepton asymmetry measurements at the LHC or the Tevatron. These are the slides that I will skip for now, which I can come back to that. But roughly speaking, there are measurements at these colliders which can probe similar combinations. Okay, and now you could ask me, well, why do I tell you about this kind of old history about this D bar over U bar? Well, the answer is that actually we still didn't decide what is D bar over U bar at X of, let's say, of about 1.15. Well, first of all, if you take this new Sequest measurement and E866 measurement, well, they sort of agree, but they don't quite agree with each other, right? And then there is another interesting result, which was published, actually a couple of them published in the last year, that say that at least in some analysis of the LHC data, if you try to extract D bar over U bar, and let's again focus on 0.15, well, you can get an analysis where you get D bar over U bar equal to 1. Okay, so therefore, well, there are these new analyses that say, well, are you sure there is this kind of asymmetry between D bar over U bar in this region? Okay, and so this is not a closed case, and something that I would like to report to you. This is a completely new result. Actually, well, the student will publish it in actually the preprint will probably be coming out next week. The star measurement here at Brookhaven can measure this D bar over U bar ratio separately, with regardless completely independently from nuclear effects. And there is an analysis of the of the measurement of the ratios of W plus to W minus cross sections that shows that D bar over U bar is of order 1.3 in the region, which actually this X equal to 0.15 is kind of sitting in the sweet spot for the star measurements. So okay, so therefore stay tuned. So basically, this is one example that even when D bar and U bar are known quite precisely, you could have many measurements that do not necessarily agree with each other. And so that's actually a challenge for us to, well, if you really try to decide what is the structure of these PDFs, well, if we need to work with many experiments, and the experiments do not have to agree with each other. And so there is lots of kind of detective, investigative work going on to understand if the experiments measure the same thing, but they don't agree. So what do you do about it? So does it mean that one experiment rules out another experiment? Does it mean that you need to combine these experiments together and be more conservative with the uncertainties? And that's where some of these subtleties related to information theory come in. Okay, so therefore, well, we will know how big the D bar minus U bar asymmetry in the proton is after we put all these measurements together and we try to see how well they agree inside the global analysis. Okay. Now, the last slide, I actually probably do not have time to talk about it. I have a few slides about jet production, but let me save them probably for the discussions. Obviously, there will be measurements of jets at the EIC as well. Except now, jets are very important for constraining the gluon PDF inside the proton. And at the EIC, an interesting challenge is that the jets are not fully developed. So when you say jet, we believe, well, basically we assume that there are tens to hundreds of particles inside the jet, right? But the EIC, the jets will not be so fat, so they will only have a few particles. However, they can provide lots of interesting information about the structure as well. Okay, and so maybe let me just go to recap. So I guess the important messages from this lecture is that, so pattern distribution functions are very important, right? So they arise in any kinds of calculations that rely on the method of collinear QCD factorization. So they are, at the lowest order, they are related to probabilities of knocking out partons with certain momentum fractions inside the proton at high orders. So they're not exactly the probabilities, but they still remain close to this probabilistic interpretation. So we cannot compute them systematically yet, except in some limited X ranges in lattice QCD. Right? But they are universal, meaning they are independent from the scattering process, hard scattering process, and they obey perturbative T-club equations, right? And so therefore, what you can do is to go through this procedure of the global analysis. I outlined some of its steps that you can measure these PDFs with uncertainties in a few select experiments and compare them against other experiments or to apply them to make new predictions. Okay, and so then tomorrow we'll discuss how this big picture evolves as we move towards the EIC physics.
You so a lot of the end of this, we were talking about the SU, the isospin asymmetry stuff. I know that there's some stuff coming out about like how there's some potential on like particle-antiparticle symmetry breaking, especially like the baryon junction stuff. Can you see something similar in CFWorks, or is that a little bit beyond what we were talking about here?
Yeah, I'm not sure which measurement you are talking about.
I might be making something up that I half remember. Then that's entirely possible.
Right.
But I feel like I remember seeing something around. Some people are saying that the baryon junction stuff leads to a higher production of baryons and antibaryons at certain rapidities.
Yeah, for example, for the let's see, for the intrinsic charm production, that will precisely be a mechanism where you should see the CPDF should be different from C-bar PDF.
Okay.
Really, there is an intrinsic mechanism that comes through this precisely this kind of. I guess it will be more final state interaction rather than initial state interaction.
Thank you.
Right.
So you said before the instanton contribution, but actually there are results that I don't know that prove that instanton actually contribute to PDF or structure functions, or.
Well, okay. So I listed several models that will introduce the difference between U bar and D bar. Now, of course, some of these models are less likely. And so the instanton model is probably less likely than, let's say, the meson cloud model in explaining the D bar or U bar asymmetry, right? But in principle, okay, so there are papers that said, okay, so this asymmetry can be produced through this instanton mechanism.
Mm-hmm.
Yeah.
More about how we actually like obtain these extrinsic and intrinsic PDFs, how we can resolve that.
So how we obtain them? Yeah, okay. So basically, again, this is actually can be a long discussion, but roughly speaking, okay. So there is a substantial depth in it if you start thinking kind of systematically. Let's take the proton as an example, right? So the proton, well, at low energy, you say it consists mostly from U and D quarks. So then you ask, how do you produce the charm PDF for the proton? Well, if you go to a very high energy, so now you zoom in on a U quark, kind of a big quark, but now you increase resolution. So for a short time, you may see CC bar pair emerging from the gluon field around the proton. And so then you must introduce the probability for finding the charm PDF through this kind of process where you emit the gluon and then it splits into CC bar pair. And actually, the DGLAP evolution will predict that there must be such a contribution. Okay, but then you can have other kinds of situations. Well, let's say the proton for a very short time it fluctuated into a 5-quark state, right? So it's the wave function now has this additional component which has 5 quarks in it, and so it goes through some non-perturbative mechanism. And it may happen that there are certain the C quarks actually are sitting in this five quark state. So therefore, if at that moment you hit the proton with the photon, well, you will see these quarks. Well, they are really behaving more like a part of the wave function of the proton. Now, the way you can distinguish them is that these contributions will have a different shape in X, because roughly speaking, if you have a massive quark inside the proton that communes with the whole proton, so the kinematics will tell you that the probability for knocking out this kind of intrinsic quark must peak at large X. For the extrinsic PDFs, the probability must peak at small x. Okay, and so that's one way that you can try to distinguish them.
I think I just need more like distinguish them, like when you actually, like I guess on the next slide, is there some actual data for like kind of resolving this difference between them? How is that actually, like, how do you separate those contributions when you're analyzing real data?
Yeah, okay, so these are not the real data though. So this is the simulation. It looks like the real data. So let's see here what happens here. Basically, the real PDF is this one, X U bar plus D bar at CT10, right? So this is what is found from the measurements. So then there is a prediction given in this paper that now tries to calculate components of this whole contribution, the U bar plus D bar, using so-called connected and disconnected contributions to the proton wave function to the PDF okay, so they are estimated in a certain way, and you see they have this precisely different shape in the behavior, right? So okay, so now this is a simulation, right? So like again, so basically like the actual PDF does not have its own uncertainty here, right? And this is more explaining the concept that you could see this kind of separation if you measure the blue curve more precisely. Yes. Did I answer a question?
Yeah, so because PDF has a scale, so when we say D bar is over U bar, it's true for all energy scale or within some.
Say it again.
Yeah, I mean, because PDF has an energy scale.
Yeah.
So when we say D bar is over U bar, so it's true for all scale or.
Well, of course, this ratio will evolve, right? But then what you will see is that basically these evolution effects, well, they will more or less they cancel to a good degree in this ratio, right? But it is true that D bar over U bar will have a different value, different scales, right? So therefore, now again, if you compare this shape at 2 GeV versus 100 GeV, does not change much. It changed a little bit, but yeah. So you must specify the scale where you discuss it. Yeah.
Would you expect this ratio to go to 1 as the scale goes down, way down?
Well, that's the point. I think it should not go to 1.
Okay.
Right. So because
So it's
I'm not entirely sure. This is maybe somebody else can answer. Yeah. So the point is that again, like for example, this separation is really a low energy effect here, right? So like between D bar and U bar, right? So therefore, yeah, it does not have to vanish when we go to low scale.
So this fluctuation in the wave function of the proton is not scale dependent or energy dependent.
No, it is all this energy dependent, but again, so there are estimates. They say, okay, now even at small scale, you may have such an asymmetry.
Yeah, the questions. So let's thank Pavel and Matt. Before we go to coffee break, we heard that it was